Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm associate professor in the Stewart School of Industrial and System Engineering. This lecture is on modeling heteroskedacity. And in this lesson, I'll introduce an extension of the ARCH model, the so-called generalized ARCH model, or GARCH. The ARCH model, while easy to understand and interpret, it has some limitations. The ARCH model is rather restrictive in that the model assumes that positive and negative shocks have the same effect on volatility because it depends on the square of the previous shocks. In practice, however, it is well known that many economic and financial indicators, but also other phenomena or other measures with time dynamics, respond differently to positive and negative shocks, particularly because negative and positive shocks may be of different nature. For example, some negative shocks can be political or environmental, while some positive shocks can be economic-driven. Moreover, ARCH models are likely to overpredict the volatility because they respond slowly to large isolated shocks to the return series, and because when modeled with ARCH, large variance effects disappear quickly, certainly no longer than the ARCH order, the specified ARCH order. Given that the impact of high variance may last for a longer period of time, we would prefer a model in which the impact of large variance can be expressed for much longer than the order of the model equations, of the order of the ARCH. Last, the ARCH model does not provide any new insight for understanding the source of variations of a time series. It provides a mechanical way to describe the behavior of the condition of variance. It gives no indication about what causes such behavior to happen. Such limitations can be addressed with a more general model GARCH or extensions of this model, as we'll see in a different lesson. GARCH stands for Generalized Auto-Regressive Conditional Heteroskedacity. The intuition behind this model is that it is a weighted average of past squared residuals, but it has declining weights, which never go completely to zeros. Hence, it models the impact of large variance for a longer period of time than the specified orders. The most widely used GARCH specification asserts that the best predictor of the variance in the next period is a weighted average of the long-run average variance, the variance predicted for this period, and the new information for this period, which consists of the most recent squared residuals. Such an updating rule is a simple description of an adaptive or learning behavior. For ease of understanding, I'm presenting on the slide the simple GARCH1 model, which often is sufficient to model heteroskedasticity. The conditional variance sigma t squared is modeled using the lagged squared noise process zt-1, similar to the ARCH model, but also includes additional lagged relationship with past variability through sigma t-1 squared. This addition allows for modeling the impact of the variance for longer than an order 1 ARCH model. More generally, a GARCH M and N with orders M and N, that is of AR order M and an MA order N, is when the conditional variance depends linearly on the lagged squared noise process through zt-1, zt-2 up to zt-m, but also through the past variability through sigma t-1 squared up to sigma t-n squared. Thus, the interpretation of the two orders is as follows. M refers to how many auto-regressive lags or ARCH terms appear in the equation, while N refers to how many moving average lags are specified, which here is often called the number of GARCH terms. This model was introduced by Boleslav in 1986. If ZT is modeled by a GARCH model, then zt squared is an ARMA process, but not with IID, or independent identically distributed white noise. The volatility of the zt squared cannot be observed fully since it depends on the lagged zt squared time series. In this example, it depends on zt minus 1 squared. Thus, we express zt squared as the sum between the volatility and omega t. Starting with this formula, we can replace sigma t minus 1 squared with zt minus 1 squared minus sigma t minus 1 squared. Separating the terms in zt minus 1 and omega, we have an ARMA 1 process. Adding together the terms with zt minus 1 squared leads then to an ARMA model in zt minus 1 squared, where the error coefficient is gamma 1 plus beta 1 and the MA coefficient is minus beta 1. Given that yt is the sum between the mean mu and the GARCH process of orders 1 and 1, then yt is stationary if its expectation mu is constant for all time points. The variance of yt, which is equal to zt, is also equal to zt to the variance to the expectation of the zt squared, is computed as on the slide. From this derivation, we have a condition in the marginal or unconditional variance of yt and the GARCH coefficients gamma 0, gamma 1, and beta 1. Specifically, the unconditional variance is equal to gamma 0 divided by 1 minus gamma 1 minus beta 1. For this variance to be finite and positive as required for stationarity of yt, we need to have that 1 minus gamma 1 minus beta 1 to be positive, or the sum of the two coefficients to be smaller than 1, and that the two coefficients are also positive. The last condition is that the covariance between yt and yt minus 1 is 0. That is, yt and yt minus 1 are uncorrelated. Note that this does not mean they are independent. In fact, for a GARCH model, they are not independent. Last, I'll point out that the second and the third conditions will be different for other orders of the GARCH model. These are some important characteristics of a GARCH 1.1 model, one of the most popular models for modeling heteroskedasticity. The first condition was derived in the previous slide, and it guarantees stationarity. The second characteristic is that GARCH models capture volatility that comes in clusters, that is, periods of high volatility followed by periods of low volatility. Last, the GARCH model has heavy tails measured by the quartices, that is, the quartices is larger than 3. If we have this condition on the GARCH coefficients. A heavy tail distribution means that GARCH can capture outlying periods of large volatility, large variability. We can expand the GARCH model by considering joint models, for example, ARMA GARCH models. For an AR1 GARCH 1.1 model, the model equations are on the slide. YT is modeled by an AR1 model with error coefficient 5, whereas the noise ZT is modeled by a GARCH 1.1 model, which means that the variance of ZT sigma t squared follows the formula of a GARCH 1.1 model. Another example provided on the slide is the ARMA 1.1 with GARCH 1.2 joint model for illustration of such joint models. The estimation of the parameters of GARCH models is the maximum likelihood estimation approach. The parameters to be estimated are the coefficients gamma 0, gamma 1 up to gamma n, and the coefficients beta 1 up to beta n for a GARCH model of orders m and n. If we assume normality, the conditional likelihood function of yt given a past history up to time t can be expressed as a normal distribution with mean 0 if the mean of yt is 0 and variance sigma t squared. The PDF, the probability density function, is as on the slide. If we replace sigma t squared, the conditional distribution, the conditional distribution, is now a function of the GARCH coefficients. As we discussed in the first lesson of the first lecture of this course, we commonly estimate such models by using a conditional likelihood, which will be the product of such conditional distributions. As you would expect, maximizing the resulting likelihood function is very complicated, requiring numerical algorithms. This is why when we estimate GARCH models in R, it can take a minute or two to get the fitted model. There are also different numeric algorithms that can be used. Some can be slower, but reaching convergence. Some are faster, but not guaranteeing convergence. This is the case for the two implementations of the GARCH model as discussed in the previous lesson. In summary, in this lesson, I introduced the more general GARCH model, the generalized arch, which will apply with a data example in the next lesson. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the School of Industrial and System Engineering. This lecture is on modeling heteroskedacity, and in this lesson, I will illustrate the implementation of the GARCH model with a data example. We'll return to the data example in which we model the stock price of PDCE Energy, the company that is a producer of crude oil and natural gas in the United States. Daily stock prices for more than 10 years of data, starting with January 2007, are considered in this data example. In the previous analysis of the PDCE price return, we first fitted an ARMA model with the selected orders 5 and 6, then applied an ARCH model to the residual process. We also compared to a joint ARMA-ARCH model. Here, we consider modeling the return price using a joint ARMA-GARCH model. We fixed the ARMA orders to be selected, the selected orders 5 and 6, using the AIC approach from the previous lesson. We'll next select the order of the GARCH model. To select the orders, we loop over all combinations of orders M and N with values between 0 and 3. Note that we consider somewhat smaller orders for GARCH than we use for ARMA modeling, since a small GARCH model commonly is sufficient in modeling the volatility. In this implementation, I first defined the model's specifics through the uGARCH spec R function. The model specifics are as follows. The ARMA orders are 5 and 6. The GARCH orders are M and N. We consider the mean to be non-zero, and we assume the t-distribution instead of normal distribution through the specification, the option distribution dot model. Then the model is fitted using the uGARCH fit with the formulation specified by the specifics in a previous in a uGARCH spec. Note that this is yet another R function or another R implementation that can be used to fit a joint ARMA-GARCH model. This R function is available. The R functions used on this slide are available in our uGARCH library. This implementation, this library, this is one, if not the most recent implementation of the ARMA-GARCH model. It provides many more modeling options for modeling the conditional mean and the conditional variance jointly, as I will show in the rest of the lessons of this lecture. Instead of using the AIC, I now use the BIC, since BIC prefers smaller, less complex models. And thus, we fit, and this is important because we fit an ARCH-GARCH joint model, which is already very complex. The final order will keep the values of N and M because BIC does not get smaller for larger values of M and N beyond the selected orders. The selected orders in this implementation are the AR order or M equal to 1 and the MA order or N equal to 2. However, when fitting ARMA-GARCH simultaneously, jointly, we should determine both the ARMA and the GARCH orders jointly. If the process is indeed well approximated by an ARMA-GARCH model, then considering the conditional mean model ARMA while neglecting the conditional variance model GARCH, as we did in the first implementation, will lead to inefficient estimators. Similarly, when considering the conditional variance model, you should not neglect the model for the conditional mean. This is because neither the conditional mean model nor the conditional variance model can be estimated consistently if taken separately. Joint estimation will typically be more efficient and this is why it is preferred. Unfortunately, the task of jointly determining the ARMA and GARCH orders is difficult, so it will require fitting many more models. For example, if we assume orders from 0 to 5 for both orders of the ARMA, the AR and MA orders for the ARMA for the conditional mean, and orders from 0 to 3 for both orders of the GARCH for the conditional mean, we would have to fit 576 models, ARMA-GARCH models. Fitting an ARMA-GARCH model is computationally expensive, and thus, without distributed computing, fitting all models will take more than a day of computation time. Alternatively, we can select the order for ARMA and GARCH separately, but refine the order selection through multiple refinements. Thus, here, we'll apply order selection for ARMA given the selected orders of GARCH in the previous slide. That is, we fixed the orders for the GARCH to be equal to 1 and 2, and now select the orders P and Q for ARMA. I apply the same code as in the previous slide, except that now I'm varying the orders for ARMA. The selected orders for ARMA are 0 and 0. That is, the conditional mean does not depend on time. Next, I refine the orders of GARCH assuming an ARMA 00 as selected in the previous slide. The selected GARCH is the classic GARCH 11 commonly used to model stock price returns. Let's now compare the three models. We have the three models are as follows. The the joint model where the ARMA orders are 5 and 6 and the GARCH model are 1 and 2. The second model is when the ARMA orders are 0 and 0 and GARCH orders are 1 and 2. The third model, where the ARMA orders are 0 and 0 and the GARCH orders are 1 and 1. We'll compare with respect to the AIC, BIC, and other information criteria. We can compute the information criteria of a model estimated using the uGARCH fit from the library RUGARCH using the info criteria command, R function. This function it applies only to models fitted with the uGARCH fit from the RUGARCH library. The output is here. The first two values are the ACA-IC information criteria or AIC and for the Bayesian information criteria or BIC. For example, the values across, in this example, the values across the 4, 5 criteria are very similar for the three models. Since we prefer less complex models, we would choose the last model where we have an ARMA with orders 0, 0 and a GARCH with orders 1 and 1. These are the ACF plots for the residuals and the squared residuals of the selected model, of the less complex model. Based on this plot, the ACF of the residuals resembles the ACF plot of the residuals resembles the ACF of a white noise. However, this is not the case for the squared residuals, suggesting that a higher order GARCH model may be considered. The R code on this slide is for obtaining the predictions for the conditional mean and for the conditional variance or for the so-called volatility. The prediction is performed one lag ahead on a rolling basis starting beginning of 2017. The code on the slide is for the first model, but I applied the code to obtain the predictions using the other two models also. The output of the model consists of forecasts for the return price, for the conditional mean, and the conditional variance. These are the prediction accuracy measures for the conditional mean based on the three models. Model 1 performs best across all measures. This is the R code we can use to compare the predictions to the observed data using a visual display. From this R code, we see that the predictions for the conditional mean are close to the zero line. This is because in this example, the volatility predominates over the conditional mean. In this plot, I'm contrasting the squared time series with the predictions for the conditional variance. And this is the plot. The predictions capture some of the volatility. However, all models consider underpredict the conditional variance, the volatility. In summary, in this data example, I illustrated the implementation of the GARCH model with the data example. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is on modeling heteroskedacity, and in this lesson, I will conclude the introduction of the concepts of GARCH modeling with other extensions of the GARCH model. A first extension of the GARCH was introduced because of one of the limitations of GARCH, particularly the residuals from GARCH models often display fat tails, suggesting that a distribution with fatter tails than the normal distribution should be considered, for example, the t-distribution. We have seen this illustrated in the modeling of the conditional mean using GARCH and t-distribution for the return price of PDCA stock price. In 1991, Denny and Nelson took this idea further by proposing a model with a transformation of the conditional variance, specifically the log transformation. Thus, according to this model, called also eGARCH or exponential GARCH model, the log of sigma t squared is modeled using a GARCH formulation. This transformation deals with also asymmetric tails, since the model allows the variance to have asymmetric behavior to reflect any asymmetries in the data. This addresses one other limitation of GARCH, particularly the GARCH models the impact of positive and negative shocks similarly. Another model which allows for asymmetry in the impact of negative and positive shocks on the volatilities is AP-ARCH. The intuition of this model is that for some time series, large negative observations appear to increase volatility more than do positive observations of the same magnitude. This is called the leverage effect. The solution is to replace the square function with a flexible class of non-negative functions that include asymmetric functions. The AP-ARCH model is an arch model formulation for the conditional standard deviation. Specifically, it models the power of the standard deviation. If delta, the power, is equal to 2, and the coefficients in the AP-ARCH gamma are 0, then we have the GARCH model. Another extension of GARCH is the integrated GARCH, which applies when the conditional variance is non-stationary. The difference between GARCH and iGARCH is that GARCH parameters add to 1. The most popular is iGARCH with orders 1 and 1, as presented on a slide, where the coefficients for zt-1 squared and the coefficient for the lagged variance is sigma squared at t-1 add to 1. But eGARCH, AP-ARCH, iGARCH are just 3 of the many other extensions. The rest of the slide points to many other references where such extensions have been introduced. In summary, I concluded the lecture on concepts of modeling heteroskedacity with extensions of the GARCH models. Thank you.